start recording. You can find my notes. So find my notes for this course at www.tutor.ca/notes. I finished it today, so there's everything up until Divergence Theorem. And yeah, so hopefully that'll be helpful. As always, I have my candle for a little motivation. I'll move this. And yeah, let's wait about 2 more minutes for people to join. Nice to see lots of people. So how's everybody feeling right now for the test? What's the candle smell? I honestly don't know. Oh, it's some kind of cookie, something. Sugar cookie. I think that's what it's called, sugar cookie. But I cannot smell it. It's worn out now. I'll respond to you, please. So someone's asking, how am I studying for COA 318? Well, I'll be doing a live session tomorrow, and I have a good set of practice problems chosen for that. With the help of Caleb once again, and from there I will be doing just a lot of those practice problems. Pretty much that. Typing my notes, going through some of the problems that were in the lectures, and then my live session where I'll do lots of practice problems there. So yeah. Programming is a little bit of a tricky one, I guess, to do for that course. Got a private message. Hey, feel okay for everything except Stokes Theorem. Yeah, Stokes Theorem, I agree, is pretty much the hardest of the 3 theorems. But we'll do an example right at the start. So I'll show you in general. Okay, it's 6:10, so we can get going. So generally, my plan for today is to verify Green's theorem. Verify Stokes Theorem. And then I don't really have a good example for verifying Divergence Theorem. So we'll just do a Divergence Theorem example. But this process of verifying, what that essentially means is like I get an example, right? Some actual example of like some sort of shapes arranged, right? And then, set up the Green's theorem equation, which is saying like this type of integral is equal to this type of integral. And then we do each separately and show that they result in the same number. This doesn't prove anything, but it verifies the fact that it's true for this situation. And so yeah, I have some good examples for that. And Stokes theorem is one of the ones that I got working. I found one that worked and I can explain it properly. Divergence theorem, I spent a long time. I don't know. We'll try it. I mean, I can do one for like a 6-sided cube, and then I would have to do 6 surface integrals, and that would not be very nice. That would be a waste of time. So, okay, let's. Is there any questions before we begin? But anything related to the course material or anything else like that before I get started? I'll give you a second. Otherwise, we're gonna start by verifying Green's theorem. Verifying Green's theorem. I'll just write it here. Just say Green's. Okay. So if you take a look at my notes, right, which I have here, then hopefully you can see them. Can you see them? Can you see the notes?
Yeah, we can see them.
You can see them. Perfect. Okay. So Green's theorem is down here somewhere. Obviously, I know I'm skipping a lot, right? So the last test ended with chapter 1. We're going to go chapter 2. I know I'm skipping a lot there, but doing these last, like verifying these theorems is practicing so many things, right? So definitely that'll be good. That'll be good to, we'll get a lot done there, right? We'll do double integrals, we'll do everything like that. Anyway, so Green's theorem here is essentially, this is in circulation form, right? So it's just telling us about the line integral around a shape here. Do I have a picture? Yeah, I have a picture. Okay, so if you want to find, right, if you want to know a relationship between the line integral around a boundary, right, and then some integral, double integral within the inside of it, that's what the circulation form of Green's theorem is talking about, right? And there's a very common trend in all of these calculus theorems that, to know some information about some integral, you just look at the boundary of that integral, right? That's what we were talking about in the fundamental theorem of calculus in Calc 1, where you just know, A and B, the antiderivative of A and B. So knowing some kind of derivative, this is some kind of derivative, which we'll talk about in a second, right? Integrating the derivative gets you something just related to the function itself. So that'll make more sense hopefully when I summarize everything at the end. But for now, let's take a look at the example that I have. So I got to just quickly open up the textbook I use. Now, of course, as always, I use this textbook for most of my learning. I mean, I use the actual course one too a lot too, but this is a very good one as well. Advanced Engineering Mathematics. So if you want to get a copy of it, just let me know after. Sorry. But for now, let's take a look at the Green's theorem part, and there is a good example of verifying Green's theorem. Oh, where is verifying Green's theorem? Let me remember where I found that. X squared. Yes, this one here. Okay, so this is actually not verifying Green's theorem, but it's an example, like that's what I'm going to do with it. The example is not written like that, but that's what it is here. So the question is written, evaluate this, integral. Oh, there's a chat message. I am recording. Thank you for checking. I am recording though. Good. So evaluate this surface integral where C consists of the boundary of the region in the first quadrant that is bounded by the graphs y equals x squared, y equals x cubed. Okay. So what I'm going to do is I'm going to set up the Green's theorem equation for this, right? So essentially this, if I just label right now, this notation here is all that's saying is that I have some vector field, right? I have some vector field x squared minus y squared 2y minus x, right? It's just a two variable vector field. And Green's theorem is just for two variables, 2 dimensions, I mean. So I have this vector field, right? And I want to know the flux, right? Well, sorry, and I want to know the flux through this boundary, right? Or that's created by this region here, right? So if I have the boundary now, if I just draw that quickly, right? So it's going to be, your x and y axis, you have y equals x squared, and then you have y equals x cubed, which is going to look kind of like that. Well, not like that, actually. It's going to look something like more like that. There. Let's just say it looks like that. So there's our point of intersection. That's y equals x squared. That's y equals x cubed. And so if I were to zoom this in, or maybe make a better picture, I'll just use the textbook's help here just to make a better picture, right? It would look something like this, right? That's the region that's created here, right? And it's important that we write the region as with clockwise bounds, right? So this bound like this, right? The bottom bound is going up, right, from left to right, and the top bound is going from right to left. And that's important because you have to have a circulation. That's the point of this little symbol here, right? The little circle on the integral means it's just emphasizing that you're doing a circulation. Okay, so the Green's theorem equation for this would then be that the integral, the line integral, the circulation, I guess, of f dot dr is equal to the double integral over d. D is that, well, I guess I'll call it r because we have a label r here. Okay, so I'll call it r. Okay, of qx minus py, not ry, py. And I'm just going to compare this to how I did it before, just to make sure I didn't make any mistakes here. Let's just see that here. Yes. Okay, perfect. So to verify Green's theorem, now this is the situation we're given here, right? To verify Green's theorem, what we're going to do is we're going to calculate this, and then we're going to calculate this separately, and I'm just going to show that they're equal, right? Because of course I could do this pretty easily just by applying, like, one of them is much faster than the other, right? But the point is that I also want to practice doing these different kinds of integrals, and this is a good opportunity to do that. We can check that we did everything right by getting the right answer at the end. So, it doesn't really matter which one you do first, obviously, right? So I'll just say this is, this is the line section, and this is the double section, right? So I'll start with the, I guess I'll start with the double integral part first. Okay, start with the double integral part. So we're going to check that. We're going to see what answer we get for there. So I'm doing the double integral over r of, and now I have to determine what qx minus py is. I'm going to take my function, my vector field. All right, this is my vector field. I'm going to leave that on the side, right? So p is equal to x squared minus y squared. Whoops, x squared minus y squared. Q is equal to 2y minus x. And so qx is just the partial derivative with respect to x, right? So it's just going to be -1. And py is just the partial derivative of p with respect to y, so -2y, right? Because the constant terms cancel out. Well, they just go to 0. So from here, I'm just going to do the double integral of qx, -1, right, minus py, -2y, okay, and then dA, right? The point is that we can turn this into, oh, sorry, I left dA off here. I don't know why I did that, right? And so this right here, this is Green's theorem. Oops, Green's theorem. So I got to do this integral, right? This double integral. It's not too bad. First, I'll just simplify the inside a little bit. So it's r, so it's going to be -1 plus 2y, right? dA. Okay, and then when we're in rectangular coordinates, right, dA is just, you know, dx dy, dy dx. It doesn't really matter. So I'll do dy dx. Okay, dy dx. In general, you want to do like the complicated bound first, right? So our y bound is the complicated bound. Our x bound is not very complicated. So what you want to do now is you got to look at the picture. Well, you don't technically have to, but a lot easier when you look at the picture. We got to figure out the bounds here. So we say, okay, well, y is coming first, right? Y is first here. Like dy is the thing we're integrating first. So I got to ask, okay, well, looking vertically like this, right? That's the y-axis. Y in this region R goes between two specific functions, right? It goes between x cubed and x squared, right? So we integrate y between x cubed and x squared. So hopefully that makes sense. Let me open the chat. I just realized I don't have the chat open. So if anybody'd like to say anything, but and yeah, feel free to ask questions at any time if you'd like. I'm happy to answer. So there's our double integral. Well, there's the first bound, x cubed to x squared. And then from here, okay, how do we know which one is on top and which one's on the bottom? Well, yeah, you literally just, you can look at it. You can see that that's on the top, like x cubed in this region is below x squared, right? So the bound of y goes between lower bound, the lower bound of y is x cubed, and the upper bound of y is x squared. And it's really as simple as that. And then, no problem. So then from here, now we know the y bound. The x bound, you might say, okay, well, it goes between these two curves now, right? But we've already kind of accounted for the fact that we're making these, you know, we're using these curves here. We've already accounted for that. So we essentially just say, well, x now just varies between 0 and 1. And now, of course, you know, I got 1 directly from the picture here, had this intersection point. So let me just quickly show how to get that intersection point, right? Intersection point, right? You would just set, you know, you have y equals x squared, y equals x cubed. You just set x squared equals x cubed, right? Divide both sides by x squared. You get 1 equals x. So your two solutions are, because of the fact that I divided both sides by x, I get x equals 0 as a solution, right? And then I get also x equals 1 is my solution. So of course they intersect at 0, 0, but they also intersect at 1, 1. Right, and so there's your other solution. So that's how I would get that. That's how I would get that intersection point there. Okay, and so now from here we know this. You know, x goes from 0 to 1. We just start integrating, right? So dy. Well, there's a few ways you can do this, but you know, it's really just you just go for it. I'm just curious. No, this is my first time doing a calc session since the midterm. Yeah, this is the first time. I really wish I could do more live sessions, but it's just too difficult of a semester, I'm gonna be honest. So yeah, I wasn't able to do more. But yeah, so we're gonna integrate the middle bit first. It's gonna be -1y, right? Or I'll just call it -y plus 2y squared over 2, right? Evaluated from x cubed to x squared, right? dx at the end. All right, then we integrate from 0 to 1. I'll just simplify a little bit. -y plus y squared. Evaluate that from x cubed to x squared. dx. Okay, integral 0 to 1. Okay, so now evaluate x squared. -x squared plus x to the, well, I'll call it x squared squared minus -x cubed plus x cubed squared dx. It's just going to be a big polynomial, right? So -x squared plus x to the 4 plus x cubed minus x to the 6. Let me just confirm that I got all of that right. Minus x to the 6 plus x to the 4 plus x. Yep, that's all good. All right, so I got this now. And then from here, it's just a polynomial, right? So we just say, well, it's all different powers, so there's no like terms to collect. So it's going to be -x squared over 2, x cubed over 3, plus x to the 5 over 5, plus x to the 4 over 4, minus x to the 6 over 6, evaluated from 0 to 1. So it's negative 1/3 plus 1/5 plus 1/4 minus 1/6. Okay, should all have equal signs at the start of all these lines. I don't know why I didn't do that. Just to be clear. There you go. And then 7, not 6. Yeah, that makes sense. 7 over 7. Thank you. Yep. And then I'll just plug this into my calculator, and I'm fairly certain we'll get the right thing. So negative 1/3 plus 1/5. Oops. Plus 1/4 minus 1/7, and we get, yes, negative equals negative 11 over 420, and that's correct, right? That is correct for everything here. I just got here. Is this the first example we're going over? Yeah, this is the first example. So we're verifying Green's theorem. I'm going to calculate the left-hand side and the right-hand side separately of this based on this question, and I will show that we get the same answer, although one is easier than the other, right? So that's the point of these theorems, is that one's easier than the other, so you can convert between them. Okay, so there you go. That's the answer for the left-hand side, negative 11 over 420, and so we're going to get the same answer over here, right? Of course. But I got to show that. So I will. Oh, sorry, I said the wrong thing. We just did the right hand side. We just did the right hand side here, and then we're gonna do the left hand side now. For Green's theorem, will the question give the field always in the form dx dy terms? Not necessarily. No, not necessarily. So sometimes it just says, it might say f dot dr, and f is equal to whatever p q r. This. Saying that is exactly equivalent to saying p dx plus q dy plus r dz, right? They could give it to you in either one, really. I don't know, really, which one. They can also give you just a function, and then you find the gradient of it. Yeah, you could the gradient field of it. We can do an example like that, yeah. We can do an example like that. I don't have one like that, but we can do it, yeah. Okay, so there we go. So that's a double integral. So you see that even though we're doing chapter 6 content, we're still practicing chapter 5 content. Now let's do the line integral part, which is just chapter 6 content, right? So I will separate that here. Right, so above there is doing the double integral, and below is doing the line integral. Okay, so the line integral, let me make sure, did I copy that? Come on. There we go. So the line integral, I got to get the information again, right? I don't want to scroll up and down a million times, so let me just take a screenshot of just, not a screenshot, but just copy this information down. Well, I guess really all I need is that, and that, and that. No, doesn't let me do it. Okay. There's F. And there's these two. Okay. That should be good. So. This is that. Okay. So now that we're doing the line integral, well, I need to evaluate it on these two lines here, right? So when we're doing a line integral like this, it's a circulation, but it has to be broken up into two line integrals, right? So C, right? C consists of C1 and C2, right? The two different pieces of it. You can't do it all in one go there. Well, I mean, actually, you can using Green's theorem, but just using line integrals, you can't do it all in one go. Sorry. So obviously, I was, some people might know, I was sick last week, and all I have left is a cough. I don't know why, but anyways, so I might cough a few times. We're gonna break this up, C1 and C2. We gotta parameterize C1 and C2 to be able to do this line integral, right? So the way I like to do it, right, it's really easy if you just have like a explicit, but if it's written nice like this, like y equals something, right? So then it's just gonna be r of t equals t, well, it's C1, so it's gonna be t cubed, right? And this will trace out the curve, because essentially you just said x equals t, so y equals t cubed, and there you go, there's your parameterization. And C2 is going to be r of t, I guess I'll call it r1 and r2, r2 of t, t squared. So in general, if you have some sort of y equals f of x, right, then you can parameterize this by saying t f of t. And even more generally, if you have some sort of z equals f of xy, which we'll talk about in a second, you can parameterize this as r of uv equals uv f of uv. Okay, but this is in general for later. We'll talk a little bit more about this, but yeah, that's in general. Right. Okay, so any questions about how I parameterize the curves here? Take a sip of my water. Okay. Sounds like we're good. So now I want to break up. So I'm going to do this integral. This integral here. It's the circulation integral of f dot dr, right? Over c. Well, I have to break that up into two, right? The just line integral over c1 of f dot dr, right, plus the line integral over c2 of f dot dr, right, of f dot dr. There we go. So now I always have to look at my notes because there's so many formulas. I just want to make sure I don't do it wrong. Now we got to know how to do these line integrals. So to do a line integral like this, I think I scrolled too far. Obviously, it's in my notes. Let's just see here. Yeah, there we go. I'll find it here. Okay, well, I mean, essentially, all you have to do is replace all the, I mean, these variables are very telling of what's going on here, right? So, oh yeah, sorry, I have to put the bounds for t. So t goes between 0 and 1 here for both of them. Okay, and that's, I mean, just plug in the endpoints, right? So you want the first bit of here to be 0, 0, right? Let's look at C1 first, because there's a little complication with C2, right? Integral of px, pdx plus qdy. Yeah, effectively, yes. Yeah. That's one way to do it, and there's just another way to do it, but effectively that's the same thing, yeah. Which is what's written up here. So here, the bounds go from 0 to 1 just because we want our first point to be 0, 0, right? So zeros, if t is equal to 0, it's 0, 0. And then if t is equal to 1, then it's 1, 1, right? So there we go. That works here. And it works the exact same way for this other one here too. The complication is that this other parameterization is going this way, right? In like order of the t, right? So t starts at 0 and then it goes up to 1, right? And that's not how we want it. We want it to be oriented that way, right? So what we're gonna do is essentially we're gonna just take the negative of this. So really it's actually gonna be the minus this integral. In fact, I'll just put it in there now, right? And that's because orientation, right, matters, right? So that top curve is oriented the wrong way based on this parameterization. It's oriented the wrong way, right? It's oriented that way. And so what effect that has in our actual solution is that we're going to subtract that amount instead. Okay, so then from here, I like to write the integral like this, but effectively, since they gave us the question, it's probably best to write it like this. I'll do one way and do the other one the other way. So just so that we get a little bit comfortable with using the different notation. So I'm going to do one with this notation, and I'm going to do the other one with this notation. Okay, again, it's just two notations for the same thing. So I'll start with the way I like to do it, which is f dot dr. So f is just f, right, which is given to us. X squared minus y squared 2y minus x. And then dr is just, well, you take the derivative, you look at your parameterization, right? I'll explain what the d is after. You look at your parameterization and you take the derivative of each component with respect to the variable. So the first one with respect to t. So that would just be 1, right? And then the derivative of the second one with respect to t, 3t squared. And then dt, your bounds are 0 to 1. Same bounds as here. Same bounds as these guys. Okay. Okay, and then we essentially have that there. So dr, effectively, I'm just going to write that. I'm just going to take a screenshot quickly. Effectively, dr, I'm going to use this. So just put that here. But, you know, let's say use That's just a convenient thing to know. Okay, and then the bounds are, again, just because our bounds are like that. So this integral, I'm going to ignore the other integral for just a second. So it's the integral from 0 to 1. Okay, we can define how the curve flows as whatever, as long as it's closed, right? If I wanted I could say top curve flows up and bottom curve flows down. Let me see. Well, yes, I think yeah, I think that would break Green's theorem. So Green's theorem assumes it's counterclockwise. I think you should, well, no, you get negative of the answer. Yeah, you would just get negative of the answer. You'd actually get negative of, let me think for a second. Yeah, you'd get negative of the answer. That's what it would be. Because if you said that, then you'd be getting negative on here and positive on here, and that's just negative 1 times the answer. Right? So it is important that it's going to be, it has to be counterclockwise, because all these theorems rely on the fact that it's a counterclockwise parameterization around the curve. So yeah, that's an important. Okay, x squared minus y squared, and then plus 2y minus x. Okay, and then so times 3t. Now the notation is getting a little bit crammed here, right? So I'm just gonna say, okay, well, dt, but I have x's and y's, but I have a parameterization, right? So I can replace x with t and y with t cubed. So this is really going to be the integral from 0 to 1 of t squared minus t cubed squared plus 2t cubed minus t 3t squared dt. Okay. So integral 0 to 1, I'll just simplify a little bit, t squared minus t to the 6 plus, I'll multiply that in, 6t to the 5 minus 3t cubed dt. Just going to make sure I'm going to follow along what I did before here, just to make sure I have everything correctly. Yes, good. Okay. And then, of course, this is just t cubed over 3 minus t to the 7 over 7 plus t to the 6 minus 3t to the 4 over 4. Evaluated 0 to 1, so it's just going to be a third minus a seventh plus 1 minus 3 over 4, right? And then we'll add that all together to be, 1 third minus a seventh plus 1 minus 3 over 4. So I get 37 over 84. 37 over 84. And is that fine? 37 over 84. Yeah, okay. And now let's do the second part, right? So I have this whole part here, right? So that's, I'll just highlight a little bit, right? That turns into that, right? And then I'll do this other part here. In fact, I guess I'll do it, I'll do it in a separate thing. Question?
Yeah, I had a question.
Yeah.
When you're converting x, y to t, you're just plugging in their parameterization, right?
Mm-hmm. That's right. Yeah, just the parameterization.
Okay.
That's cool. Okay, so then I'll do it. I don't want it to get too messy, so I'm just gonna say that turned into that, and then now separately, I'm gonna do that. I thought I would do it like going down like this, but it's gonna get too messy. So I'll do that. I'll do that here. Like I'll start. I don't know how to signify that I'm starting it there. Starting it there. Okay. And so just put it like that. It's a little bit messy to draw it like that. So how about I just go like that? There we go. Okay. Well, I guess you can see. So now I am going to do it in the other notation, right? The other notation, which is actually equivalent, right? But the other notation, it would be written like this, right? So it would be, where are we? By other notation, I mean this stuff right here, right? So p dx plus q dy. Okay, so p is x squared minus y squared, so x squared minus y squared dx plus q, which is 2y, so just to be clear, I'm going to put brackets around this, 2y minus x dy. And so now to evaluate something in this form, obviously you can also just go back to this and do it how I just did it up here, but there is like a nice way to do it from this form too. And that's to say that, you switch everything to dt. So dx, well, dx is dx by dt, right? I mean, with a little bit of magic going on there, right? But the d's cancel, and it's the same thing as dx, right? So dx dt, I can figure out what that is, right? So that's going to be So x squared minus y squared, right? dx dt, I got to look at my parameterization for the second one here. So I'm just going to copy that down here quickly. Right. That's our parameterization. I'm not accounting for the negative until the end. I'll just subtract the answers at the end, right? So that's our parameterization for C2. dx dt is 1 plus 2y minus x dy dt. That's 2t, right? And then dt at the end. Technically, there's a dt after all of these, and you can factor the dt out, right? Obviously, that's not super good math, but that is the answer there. And then also 0 to 1, right? And yeah, there we go. That's that. I guess at this point you could say 1 to 0, and that would work, and that would account for the wrong direction. But I think it's better to just always, like, that's weird to do bounds like that. So it's better to do it just like this and then just subtract your answers. But yeah, that's that. So now I'll substitute in my parameterization. So that's going to be t squared minus t cubed. I mean, it's going to be very similar, right? Sorry, not t cubed, t squared squared plus, so our parameterization is t squared for this one, right? So it's not exactly the same as the last one. So 2t squared minus t, right, times 2t dt. So integral 0 to 1, t squared minus t to the 4 plus 4t cubed minus 2t squared dt. Oops, dt. I'm going to confirm that this is correct based on what I did before. Negative 4t squared plus 4t cubed minus 2t squared plus t squared. Yeah, good. Okay, and then finally here, we're just gonna, is there any like terms combined? Yes, there is. So 0 to 1 of negative t to the 4 plus 4t cubed minus t squared dt. And this is negative t to the 5 over 5 plus t to the 4 minus t squared over 2 dt, not dt, sorry, evaluated 0 to 1, negative a fifth plus 1 minus a half. So if I do this all together, negative 1/5 plus 1 minus 1/2, I get 3 over 10. Is that what I got before? No, I don't get that. Negative plus 1. That was supposed to be over 3. Sorry, that was supposed to be over 3. A third. There we go. Over 3, 7 over 15, which is what I get before. 7 over 15. So now I go back up to my equation, right? This is what we were trying to do, right? And boom, boom. Come on. There we go. I guess I'll leave it in red, right? So the result for the first part here, that was 37 over 84. 37 over 84. 37 over 84? Yeah. Minus 7 over 15. 37 over 84, I hope, minus 7 over 15 is negative 11 over 420. And the reason this is anything special is because that is exactly the answer we got when we did Green's theorem, when we did it with the double integral, right? Negative 11 over 420. So we did it right. And so there we go. We verified Green's theorem by looking at how the left side and the right side in this particular example evaluate to the same thing when you go through it. And of course, if you were in this situation, right, and you looked at it like this, right, I would jump right to Green's theorem because Green's theorem was that long and the line integral part was that long, quite a bit more, right? Of course, you get the same answer, that's the point, but one's easier than the other. Any questions about all this? Everything I did in this question. Okay. Excuse me. So, okay, in the double integral method, what would your bounds be if it was clockwise? The double integral method wouldn't change, I don't think. Let me think for a second. The double integral, because the area doesn't change, right? So what would change here? Yeah, nothing would change. Nothing would change. The double integral method would not change. Yeah, it's just interesting that your answer would be negative. Like, it has to be negative of the other. but I don't see how that would make like I don't see where that would be in here. Like that would actually cause the difference, like in here. Because let me think for a second here. Anything going on? You would get negative of the answer though. It should be negative of the answer. Interesting. Yeah, I don't actually know what would change in here, but you don't think it shows in the calculation? You just have to. Oh yeah, that's true. That's true. Okay, so if it was oriented clockwise, the issue is not with your double integral. The double integral gets you the answer. But if you're oriented clockwise, that is causing you to get negative of the answer, right? So you'd have to multiply that by -1 to get the counterclockwise orientation. So the issue is in the double integral. Sorry, the issue is in the line integral part of that if you're doing it clockwise. But every example I've seen has been counterclockwise. They don't really try to trick you with that. So obviously, like there's certain situations where you have to account for it, like here, which is why I thought this was a good question. It's the bounds that make it VE, right? I don't know what V. Negative. Oh, it's the bounds that make it negative. It'll essentially be that, like, when you're calculating the line integral, you stick a negative in front of it, right? If C1 is like essentially, let's say C is a clockwise orientation, like C is clockwise orientation. What you're really calculating is negative C, negatives. That's what you're doing in the situation. And so you have to put a negative. So the negative here goes into the negative here. And the double integral gets you exactly what the answer. There's no way to like get the negative answer of it. There's no clockwise or counterclockwise in a double integral, right? It's just that in the line integral, if you do it clockwise, that's the wrong direction. So you're going to get negative of the answer there. Okay, more questions. So how can you tell the direction it's moving if you don't have the arrows? Well, that's going to be from the parameterization. What you're going to want to do is try to make a little sketch of the parameterization. Try at the first bound and then at the second bound, right? So I said, okay, the lower bound is, let's look at this other one. The lower bound is 0, so it's going to be 0, 0. Whoops. It's going to be 0, 0. So that's our starting point. And the upper bound is going to be 1, 1 because the t goes to 1. So that means that the parameterization is going from here up, right? You're starting at 0, 0, going to 1, 1. And so that means you're going this direction. But that's not how you want to go. You want to go that direction in this example. Let me know if you have any more questions about that. Can you explain why you had two parameterizations? I had two curves. So I needed two parameterizations, right? One for curve 1 and one for curve 2. Right? Curve 1 is y equals x cubed. Y squared is curve 2 is y squared. Y equals x squared. You see it here. Can't speak for some reason. Okay, any more questions about that? Of course, feel free to unmute if you're interested. Okay, then let's start on verifying Stokes Theorem. It's going to be a very similar process, verifying Stokes Theorem, but it's going to make us do surface integrals here, right? So that's going to be interesting. Verifying Stokes Theorem. Right, so this is a new question, brand new, question. It's going to be brand new prompt and everything. I think the verifying questions are good. I like them. A little bit mathy. Okay. Stokes Theorem. Okay, this is a good one, and this is going to be good for orientation stuff with negatives. These first two questions that I'm doing are from the other textbook. Yes, from the textbook that I use. Right. Again, if you're interested in it, just message me after, or I can help you get it. But yeah, these first two questions are, and then the ones we do after are probably from the practice test. I'll do some from the practice test. There's one in particular I want to do from the practice test, and then the rest I can just take suggestions if people want to do. But yeah. Okay, so verifying Stokes Theorem. We're going to use it. We're going to do that, using the following situation. So let S be, let me open the chat up again. Let S be the part of the cylinder Z equals 1 minus x squared for x is between 0 and 1, y is between -1 and negative 2 and 2. Verify Stokes theorem for the vector field that, assuming S is oriented upwards. So S is oriented upwards. Essentially, you just hear that and you say, okay, good. If it was oriented downwards, I'm quite certain you would just say the negative of the answer is gonna be what you get, because all the theorems assume oriented upwards. So if it's oriented downwards, you're just gonna have negative, right? And that's all about the normal to the surface, right? That's going on. Okay, let's quickly talk a little bit about what Stokes theorem is saying. I can do a little quick demonstration, right? I'm gonna need to use a little pictures that I have here though. So essentially, if you remember Green's theorem, right? Well, of course you remember it, but if you remember this form of Green's theorem, right? We could rewrite Green's theorem. There's two forms of it. So let me find the other here. This form of Green's theorem. So which is what we used, right? You can think of that right there. That's like the kth component, right? That's the kth component of the curl, right? That's essentially what it is, right? That's because if you were to calculate the curl, right, it would be that. I mean, so just believe me at this moment, right, that it's the kth component of the curl. It's kind of like the perpendicular component of the curl. And the curl is this idea of like, we can evaluate this vector field, right, at every point, and we can give it a vector at every point. And that vector represents the axis that would be spinning if there was an axis of rotation there, right? And the magnitude is related to how fast that would be spinning, right? So this is essentially saying, what this is really saying here is that the perpendicular component of the curl, right? The perpendicular component of the curl to the actual region, right? If I integrate that over the region, I get the line integral, or the other way around too. So if I follow what I'm saying here, let's say it again, but looking at this plane, right? If I integrate the kth component of all of the curl vectors inside the region, I get the line integral inside of the boundary, right? Which is again following the trend here that, you know, knowing information about some kind of derivative of the inside. Curl is like a derivative. If I say I want to take a derivative of a vector field, we have multiple ways to do that. We have divergence and curl. Those are the two ways to do that. And so curl is one of them. And so I know information about the derivative inside. So I only use information about the antiderivative on the outside to solve that, just like we do in the fundamental theorem of calculus, right? So curl is like a type of derivative here. It is like, that's not just a way of looking at it. It is like a type of derivative. Stokes theorem says that this is true even if the surface is not in the plane, right? Even if that surface right there is, or if it's not just a region in the plane, it's also true if your surface is up in the air, right? So instead of it's not just the kth component, it's the normal component of the curl, right? The component of the curl that's normal to the surface, right? Up here, that simplifies down to the kth component of the curl, right? Here, when it's on the plane. But here, it's not so simple. And Stokes theorem says that pattern continues, and it says that, the line integral of the outside of the boundary curve is equal to the integral of the normal component. Now remember, when you dot a vector with another vector, you're asking how aligned are they? So how aligned is the curl to the normal, right? Integrate that on this region, that's equal to the line integral of the outside, right? Again, curl is like a derivative, right? So we know information about the derivative, and we're finding information about the actual function there. So hopefully that made some sense. Do Stokes and Green's theorem help us find the area, or is it the flux? So I mean, just to find area, you just want to use a double integral straight for that. And then you could switch it to a line integral, I guess, after that somehow, right? But if you're just asking about, like, does it do a double integral, right? So Green's theorem turns, well, I mean, they kind of both turn it into a double integral, right? Both of them turn your line integral into a double integral. But usually you do it the other way, right? Usually you turn the double integral into a line integral. But I mean, it doesn't really, like, it doesn't matter. You can go both ways. Right, so the answer is really both that find the area. Right, but area is not exactly what we're interested in this moment. It just straight area, you just use a straight double integral for that. Yeah. Okay. So there's Stokes theorem, right? Stokes theorem is interesting. I'll just put it here. And then put that there. So we want to verify Stokes theorem for this. So what this is saying is that the line integral on the boundary of this surface, okay, f dot dr, is equal to the double integral of the curl of f, right, dotted with the normal vector to the surface, ds, the surface integral, essentially, the surface integral of the curl, right, dotted with the normal vector across that surface, right? So that's our s, and then c is that boundary. So to get a picture of what's going on, let's open Geogebra quickly here. Geogebra, right? Obviously, drawing in 3 dimensions is very hard, so let's use the calculator here. So I'll say z equals 1 minus x squared. Yeah, 1 minus, yeah, that works. Although the picture, it's weird. It glitches out a little bit. Yeah, 1 minus x squared is not a cylinder. You're right. So I guess they're a little loose with what they mean by cylinder. So essentially, if you look at, like, obviously cylinder means a very specific thing, right? So that's essentially what it is. But we're really only concerned with x is between 0 and 1. So, okay, this is by x on the negative x-axis, but let's just pretend it's the positive x-axis. So x is between 0 and 1, and y goes between -2 and 2. So -2 is over here. So we're essentially interested in just this little section of it, right? Just this little section of it. That's approximately a cylinder, right? That's approximately a cylinder there. So we will we'll use that, of course, to help with this integral. Now, of course, there's a better picture too. So let me just draw a better picture, and by draw I mean get a picture of the better picture, right? So this is, so it's not exactly a cylinder, but it is something like that. So I'll just cover that with that. Right. So it's, yeah, they're a little loose with what they mean by cylinder. So, I mean, it doesn't matter. Like, the fact that they said cylinder here, they could have said surface, and then it would be the same thing, right? So, and then we wouldn't be confused by this. So it doesn't matter that it's not really a cylinder. What matters is this picture that we've created here. So C is the boundary curve of this, right? C is the boundary curve here. And so what you want is you want to be able to do the line integral on that boundary, but since it's piecewise, what's the word? Not continuous. Piecewise, there's a word, I forget. Is it right here? Smooth oriented, piecewise smooth. There you go. It's piecewise smooth, right? Which means, you can break it up into piecewise, break it up into smooth components, right? 4 of them. We are going to want to define those. So we'll make 4 parametric equations, right? And then from there, we'll just do the line integral over them. Or we can use Stokes theorem to tell us that this is equal to the curl of f dotted with n, the surface integral of that over the surface. That's that whole surface, the blue thing there, that's all s. So we'll do that. So let's take a look at our Stokes part of this first, right? Let's do the Stokes part of it. So, I mean, that's kind of bad to say. So the part that is interesting, right? This is just a line integral. So we'll do that, but this is the real Stokes part. So I need to, first of all, determine the curl of f, and I also need to determine the normal, right? So, let's do the curl first. So the curl of f, okay, is, well, this is how you do it. You take f, okay, you do nabla, or the gradient, right, cross f, right? So that is the vector. Now, this is so partial x, partial y, partial z, and I want to take the cross product of that with my function, which is xy, yz, xz, and that's going to be the curl, right? So the way I like to do the curl is the method with the 2 lines, and you cross out things on either side. So instead of having to write partial, I'm just going to call that dx, dy, dz, dx, dy, dz, xy, yz, xz, xy, yz, xz, cross the last two out, and now you start taking components here, right? So the result is, of course, a vector, because the result of the curl is always a vector. And then, so dy xz is 0, right? The derivative of that with respect to y is 0. And then, negative, the derivative of this with respect to z is just negative y, right? Minus y. Derivative of this with respect to z is 0. Derivative of this with respect to x is z, so minus z. Derivative of this with respect to x is 0. Derivative of this with respect to y is minus x, or is x, so minus x. And so our curl is going to be negative y, negative z, negative x. And there we go. So now I found my curl. Right? Let me check. I'm just going to note how I did this before, just so I don't mess anything up here. That's fine. That's the line integral part. There we go. So I got the same thing. Yeah. Okay. All good. So what you're going to want to do now is we want to take the f.n ds. There's a quicker way of doing this. Okay. Anyways, to do this, we need to parameterize the surface now, right? So I'll label here, this was part 1. It was just to find the curl. And part 2 is we want to parameterize the surface. Let me type that here. Parameterize the surface. So let's take a better look at our surface here, right? What I know about it is that it's written as z. It's written as z equals 1 minus x squared. So because I have an explicit surface formula for it, I can just say this is r of uv is equal to u v 1 minus u squared, right? So essentially what I said up here in this purple box, right, was just that we do in general, u v f of uv. So u v f of uv is what we have here. And so that essentially means, draw a vector which goes to uv and up by whatever the function amount is, which makes sense. That's what we mean when we say this. We say, go to this point and then this point, right? That's your xy value. And how much do you go up by? Well, that's the value of the surface. So that's why the vector is going to be drawn from the origin to there using this formula like that. So then from here, we know our parameterization, which is convenient. And what we can do now, there's an easier way of doing it, but I think I want to go through it all like this. So the formula we're going to use for this surface integral, let me just draw it here. So the curl of f dot n is going to be just equal to, so double integral over s of, we figured out the curl, negative y, negative x, negative z, negative x, okay, dot n ds, right? So there's a formula in my notes for a integral like this. Surface integrals, that's a regular surface integral, vector surface integral. There it is. Okay. So if you ever have I'll just take the second half of it, right? If you have something like this, we're going to apply this formula, which is just saying that to do this, you just evaluate the vector field at the parameterization, and then you need to find these tu cross tv vectors. So now we got to figure out what those are. They're don't worry about too much about why they are what they are, right? I don't really have too good of an explanation for it. I can send you some videos if you're interested in why this is what we do, but the definition of tu, right, given some parameterization r, right, is the partial derivative of x with respect to u. Yeah, partial derivative of x with respect to u, partial derivative of y with respect to u, right? Partial derivative of z with respect to u, right? And tv is, as you'd expect, right, is going to be partial derivative of x with respect to v, partial derivative of y with respect to v, partial derivative of z with respect to v. And so where is x, y, and z coming from? That's coming from our parameterization, right? That's our parameterization. That is That is x, y, z. So and then we have to cross them, right? And then we get that. But otherwise, that's the process. Pretty mechanical after this. So TU. Any questions? No. Thought someone said something. Okay. TU is the partial derivative of x with respect to u. So that's going to be 1. Partial derivative of y with respect to u is going to be 0. Partial derivative of z with respect to u, right, is going to be negative 2u. And TV is going to be, well, partial derivative of x with respect to v, 0. Partial derivative of y with respect to v, 1. Partial derivative of z with respect to v, 0. Okay, so we get these two. I'm just going to confirm that this is exactly what I got before. Oh, no, wrong section. Yes, this is what I got before. Okay, good. So from here, let me just see. Okay. We're going to take the cross product of this. So TU cross TV is, well, this is how I like to do it. So 1, 0, negative 2u. 1, 0, negative 2u. 0, 1, 0, 0, 1, 0. Chat. Wait, so why did we find the curl? That's the curl. That vector right there is the curl. Curl F. Because essentially in here, that's the formula. We need the curl of F dot n. And so now I guess I should be clear. I'm applying this, but I'm not applying this directly to F. I'm applying this to, I'm just saying here that this is like, whatever, it's E. Say it's E. And E is the curl of F, right? The curl F is also a vector field because it's a vector for every point too.
Sorry, what's the force function? Like the force of the VVF?
This one here, which is not the same as what I'm putting into the.
No, I know. Okay.
Does that make sense?
Yeah, I'm just wondering. I'm not sure if I did something wrong, but I'm getting a different value for the curl, but I'm also using a slightly different method, I think. I'm using the determinant method to calculate the cross product.
Well, I mean, it should get you the same answer, but
yeah, so I'm not entirely sure.
But I have the text.
Take your word for it
to back me up here. So
yeah. Okay.
So yeah, that's right. Okay, so then so I'm gonna take the cross product here. So those terms go away. Did I do that right? 1, 0, negative 2u. 1, 0, negative 2u. 0, 1, 0, 0, 1, 0. Okay, so then the resulting vector is going to be 0 minus negative 2u, and then 0, 0, 1, 0. So there is our cross product, right? And so that's the answer for here. So 2u, 0, 1. Answer there. And so now finally into this formula, I can say that this is equal to the double integral of, okay, so f of r of uv, right? So that's going to be, well, it's going to be negative y, negative v, negative z, negative 1 minus u squared, right? Negative x. Oops, sorry, I didn't mean to put that at the bottom. Negative x, which is negative u, right? Dotted with, looking up here, this vector we just got, 2u, 0, 1, and it is going to just be dA. Okay, dA. And A is just the area here, right? So I'll just say over S. Sorry, not over that area. Sorry, over the parameter space. So something I always forget to do is I have to put bounds on the parameters here, right? So the way we do that is we note that, okay, so you got to look at the picture really. Let's look at our x-axis first, which is our u variable. Our x-axis goes from 0 to 1, right? So u is going to go from 0 to 1, right? On the x-axis, that's the only place we take there. And then v, very similarly, we just say, okay, well, it's going from negative 2 to 2, right? That's given to us in the question, right? 0 to 1, negative 2 to 2. So v is no different because of the way I parameterize this, right? V doesn't change. V is not some other variable there, right? It's v equals y, right? That's what I'm saying by doing this. And so I can just do that. And those are bounds. So then that is the bounds of my integration now. Right? So what I can do is if I scroll down, my notes here. right? Well, first let me calculate this dot product. So negative 2v minus u, right? And I will do dv du. Okay, obviously you can do it whichever way you want to do, but this is how I did it in my notes, so I'll just match that. And then from here, let me get it. There we go. You just set up the actual integration. So v, like I said, v goes from negative 2 to 2. Right, so dv, well, negative 2v minus u. Dv du goes from 0 to 1. Or u goes from 0 to 1, so that's why I put the bounds like that. And then now I will do this double integration. So with respect to v is going to be negative 2v squared over 2 minus
sorry.
2v. Yeah.
Why we only have negative 2v? Can you go up a little bit
Yeah.
to where we were doing the dot product? So we only have negative 2v, but isn't it 2u times negative v?
Yeah, that makes sense. Yeah, that makes sense. I don't know what I wrote. Negative 2uv. Yeah. Yes, that is what it's supposed to be. Yeah. Thank you for that. So that's uv. So then here, with respect to u, so it's going to be still going to be 2uv squared over 2 there. Yeah. Okay. Yeah, perfect. Okay, so then now I'm going to just do this. So it's going to be negative uv squared minus uv evaluated from negative 2 to 2 du. So integral 0 to 1 of, this is for v, right? V is being evaluated from these bounds. So negative u2 squared, or 2 squared, minus u times 2 minus negative u negative 2 squared minus u times negative 2 du. And I will just start simplifying some things here. So negative 4u minus 2u plus 4u minus 2u d. Okay, so of course these will cancel, and you just get negative 4 integral 0 to 1 of u du. Okay, which should just get me negative 4. Wait, I messed something up. No, I didn't mess anything up. Never mind. Integral 0 to 1. Well, actually, we can just u squared over 2 du. I always say that, not du. 0 to 1, negative 4, and this is just going to be 1 over 2, which is negative 2. And there we go. So using Stokes Theorem, I solved for that quantity. Now, we're going to do it again with the other quantity, like with the, sorry, not the other quantity, but with the other method using the line integrals, just to make sure that we get the same thing, right? And also to practice a little bit doing line integrals, which is also an important thing to practice, and making parameterizations and all that. So any questions so far about what I have done here? So that would be the answer for Wilbur. Okay. Then let's continue. We have the left side to do now, right? So I'm going to do the left side just to verify we got something that makes sense. Can I switch to that? No, I cannot. No, what's going on? Okay, doesn't want to switch colors, so I guess I'm left with that. So here, okay, OneNote's being weird, so I gotta restart OneNote.
You mentioned before about there being a faster way to get the normal vector, I believe.
There's like so here I basically didn't even get the normal vector really in this case. I didn't even solve for the normal vector because I just used this formula that we had.
Yeah, the way you do the normal vector one instead is, I think you know how you have a function for z or for z. I think you're supposed to move z to the other side of the equation, and then you call that new equation with z on the right side, you call that like g or h.
Yeah.
You know, it's something, and then you do the gradient of that. Like you find the normal vector is that being your function.
Yeah, so I'm gonna do that in the divergence part. That's the thing that was causing me a lot of trouble in the divergence part, because like I don't remember that ever being explained. It's not even in the textbook, but it is used in the solutions, even for the practice midterm. That formula is used. So practice final. So it is a little strange. I will talk about that for sure. Yeah. Okay, so let's do the line integral part. Although I don't know, like yeah, it's a lot of line integral. So we'll see how fast it's going. It is good to practice the parameterization thing though, right? So we're gonna parameterize these and we're gonna orient them the right way, right? So to evaluate this, right, I need to figure out the parameterization of all of these parts here, right? Because C, this is equal to the line integral over C1 of F dot dr plus the line integral over C2 of F dot dr plus the line integral over C3 of F dot dr, and as you might expect, the line integral over C4 of F dot dr, right? So we want to get all of these quantities separately and then add them all together at the end. So let's parameterize everything. So parameterize, right? So parameterize C1. C1, let's take a look at it. C1 is a straight line, right? Which is at x equals 1, actually. X equals 1, right? So I would say that to parameterize this, well, certainly my x value is always 1. My z value is always 0, right? My z value is always 0. My z value is how high up I'm going, right? So it's always 0. And my t value, well, sorry, my y value varies. So I'm going to put a variable, and it varies in particular between -2 and 2. So there is our first parameterization. And it is oriented the correct way, notably. It's oriented the right way. It's going from the bottom to the top there, right? So it's oriented like that. Now for C2, this session is until 8, yeah. Now for C2, we have the curved bit there. So it's also going to be an R of t, right? But let's see what's going on. So the y value this time is always 2 for C2, right? That's C2 right there. So the y value is always 2. The x value varies, right? The x value varies. So I'm going to give it a t. It varies between, 0 and 1. Yeah, it varies between 0 and 1. By keeping the things the right way. Then our z value is just 1 minus t squared, because that's what was given to us as our surface. Like our surface was z equals 1 minus x squared. So in this case, that means we have 1 minus t squared. And the thing to note here is that this parameterization is oriented the wrong way. Okay, and the reason I know that is because just think, what's going to happen if I plug in t equals 0? It's going to be 0, 2, 1, right? So 0, 2, 1. Oh, is that actually right? No, 0. No, that's not right. 0. Yes, 0, 2, 1 is right there, right? And then if I plug in 1, I'm going to get 1, 2, 0. 1, 2, 0 is right there. So it's oriented the wrong way. So whatever result I get for this integral part, I'm going to just take the negative of it, right? I want the negative of it there. So any confusion, let me know. Otherwise, I'll move on to R3. Do you think we will get the diagram of the surface of the test? Depends on the whole, because this whole question depends on it. Yeah, that's very true, right? So being able to sketch generally what's happening is an important thing too. So if I were given this, like, I would sketch it like this. I would essentially say, well, if I were to, like, on the ZX plane, it's basically a downward facing parabola, right? It's a downward facing parabola. And so if I were to extend it, then, you know, the Y value can be whatever I want it to be. Right? The Y value can be whatever I want it to be. So I'd have some sort of shape like that for sure, right? And then the bounds, I'd have to draw it in, right? So it is possible to sketch. I'm fairly certain if they give you anything to sketch, it'll be simpler than this to sketch, to visualize it, right? And so, yeah, then we have that. So then from here, if I keep parameterizing, I have R, I guess I'll call it R2, R1, R3 of T equals, so R3 is going to be C3. So again, very similar idea. Well, X stays constant. Z stays constant. X stays constant at 0. Z stays constant at 1. t varies, right, between -2 and 2. But again, that's oriented the wrong way. We don't want it to go from -2 to 2, right? We want it to go from 2 to -2. So I'm going to have to, again, take the negative of this answer here. And finally, for C4, it's going to be R4 t, which is equal to this curve right there. So it's just going to be, well, our x value varies, right? Our x value goes back and forth there. Our y value stays constant at -2. And our z value is always 1 minus t squared. And how does t vary? Well, t varies, it's our x value. It varies between 0 and 1. And in this case, it's oriented the correct way, right? We want to go from x value to 0 to 1. Remember that this is the x-axis, that's the y-axis, z-axis. So important to note there. So the middle two are going to be our negatives. So maybe I'll just do like one of them, and then I'll just tell you the answers for the rest of them. And I want to move on to some other stuff too. So let's do this middle one maybe, right? Let's do like C2, and then the rest of them I'll just tell you the numbers. How about I just tell you the numbers here? C1. See what I get. Oh, C1 is 0. This is 0. So, sorry, to be clear, the line integral C1 F1 dr, not F1, sorry, F dr is equal to 0. This one we will calculate. This one is equal to 0. So I'll say FC2, C3 F d dot dr is equal to 0. And then I'll just tell you this bottom one is, well, how about we'll calculate the bottom one just because it's the last. No, actually this one has a negative sign, so we'll do the one with the negative sign. The integral of C4 F dot dr is equal to -19 over 15. Okay, but we'll do this one. I know I'm pulling these numbers out of nowhere, right? But we'll do this one here. So line integral C2 of F dot dr is our goal. So I'm gonna have to take this whole line here. Right? So when we're doing the process, we're just gonna ignore the negative sign, right? The negative sign isn't gonna affect our calculations here. We're just gonna calculate it, and then we're gonna subtract in our answer, right? So this is what we're trying to calculate, C2 of F dot dr, right? And so now we use our actual, the F that's given to us, right? So F is, where's F? F is up here somewhere. Wow, we went far. Okay, xy, yz, xz, xy, yz, xz. And we're gonna dot that with dr, right? So dr is dx dt, right, 1. dy dt, 0. It's supposed to be a t there. dz dt, -2t. dt, and our bounds are 0 to 1. So hopefully that made sense. If anyone has any questions, let me know. That is that. And then we should get from here integral 0 to 1 of xy minus, well, 2t xz. But I'm going to want to substitute things in now, right? It's not good to have variables mixed up like this. So x is equal to t, y is equal to 2, -2t, x is equal to t, z is equal to 1 minus t squared dt. Again, that's just from the parameterization. That's why each of these would be different. If I didn't plug in the parameterization, it would just be the same number 4 times. So the parameterization is different, so that's why we get a different number. And the bounds are different, so yeah. So 0 to 1 of 2t minus 2t squared times 1 minus t squared dt. 0 to 1 of 2t minus 2t squared plus 2t to the 4 dt. And this is t squared minus 2t cubed over 3 plus 2t to the 5 over 5, evaluated 0 to 1. 1 minus 2/3 plus 2/5. Let's make sure that that's what I got. 1 minus 2/3 plus 2/5. Yes. And it's 11 over 15. Okay, 11 over 15. So we determine now 11 over 15. So I'm just going to put a little star determined this here. Okay. The other ones just done earlier, calculated earlier. Okay. And so now finally to figure out our actual final answer here, right? This, which is this. Okay. I'm just going to take all these values. So this first one was 0, 0. The next one is 11 over 15, but I need negative of it. It's oriented the wrong way. So I'm going to subtract 11 over 15. Next one was plus 0 again. Right? So minus 0, but doesn't really matter, this one. And then plus negative 19 over 15. 19 over 15. Okay? And that is equal to, let's just confirm, negative 11 over 15 minus 19 over 15 is equal to negative 2. Which the reason this is anything special is because when we did this with the double integral, the curl, we also got negative 2. So we have verified Stokes theorem by evaluating both sides and seeing that they're true. And yeah, that's pretty much it. So any questions about how I did all that? Any part of it, the first part, the second part, whatever. Okay. So I have an example for divergence theorem. I don't really have a full thing like this for divergence theorem ready, but we can try, but probably best to do some other stuff, but hopefully that made sense. Could I explain how I solve a gradient again? What do you exactly mean by solve a gradient? Solve a gradient, like figure out the potential function, like what, like a function that has that, like the gradient. So what I'm saying, a potential function is like if I'm given some field f, right? Yeah, given some field f, determine the potential function, gradient f that is equal to f. That's what you mean? Yeah. Okay. Yes, we will do that for sure. Let's do a quick example of divergence theorem, and then after that, it's all good. I think we could do the example from the practice test, I guess. I don't really have any other example for this. Honestly, the example from the practice test is very easy compared to questions in the textbook, at least, right? So that's a good thing to hear, right? That it's very easy compared to the textbook. But I don't know if we're going to be getting questions like that on the actual test, but we will see. So yeah, we will definitely do that gradient question. Let's just first do a quick divergence one, or divergence theorem. Yeah, the one on the test is just very easy. The one on the practice test is just very easy. So there's better ones for us to do. Let me give it a try here. I tried a couple questions before. A lot of issues with one. That's fine. That was really easy. 85, no. Oh, I have one where I have to convert to polar, which is a divergence question. That might be worth our time to do. Yeah, that might be worth our time to do. So probably I'll have enough time for this divergence question where I convert to polar coordinates, and then we'll do a question where I solve for the gradient, and I'll do that one directly from the practice test. Okay. So this one is number 393 from the textbook, which is assigned work, right? So use divergence theorem to calculate the surface integral that for this vector field, where S is the surface bounded by that cylinder and those two planes. So essentially, we have a, if I really struggle to draw this, we have some sort of cylinder in the XY plane, right? But it goes behind, right? So I gotta draw it behind. So there. Oh wow, could have drawn that. That's not bad. And it's going up and down, obviously. right? And so there's a circle like that. There's our cylinder. It is bounded by two planes. It is bounded by this plane, right? The x equals the z equals 0 plane, right? I'll draw a plane like that, I guess, right? And then another plane, z equals x plus 2. It doesn't really matter what plane that is, but it's above this one, so it's some other plane slicing it. Again, it doesn't really matter like how I draw that. Like it's just some other plane slicing it like that. I guess I'll draw it like that. Right, so there's my try at drawing it. Let's use GeoGebra to make a better picture just for the sake of this. X squared plus y squared equals 1. Z equals 0. Z equals x plus 2. Okay. So it looks, approximately. Well, I guess I'll just show the whole thing. There you go. It looks approximately like this. Right? So, I mean, again, it doesn't matter exactly like the angle of that. Right? We're not using the picture to solve anything, but it's just helpful to look at. So, generally, what we're trying to find is the divergence, right? Well, the surface integral for this. Right? So, I guess let me like take a screenshot quickly. I guess I'll take a screenshot. That looks pretty good. So we're going to use divergence theorem because divergence theorem tells us, it continues this trend that we're seeing with these formulas that if I want to calculate, there should be a dot there. If I want to calculate the triple integral of the volume of the divergence of f dv, right? So we're doing a volume integral here, triple integral. That's equal to the surface integral of the outside, some sort of antiderivative, right? Divergence of f is like the derivative of f prime. We're taking like an antiderivative here, and we're finding the surface integral, right? And so using boundary conditions, we can find information about the derivative inside. So that's essentially what it is. There is supposed to be a dot on there, which is bugging me, but that's okay. Oops. There we go. Okay, so that's the divergence theorem for us. So f.ds. So we're going to use this to say, well, if I'm trying to calculate that, right, I could also do the triple integral over that volume of the divergence of f dv, okay? And that is easier to do because otherwise I'd have to break this up into like a bunch of different components and then I had to find normals and stuff like that, and it's not so easy. So let's do it like this. So divergence of f is the first thing to figure out. Divergence is pretty simple, right? The way I like to think about it is like you're adding together just all the partial derivatives. So you're trying to figure out, how much is the function spreading at that point, right? That's what the divergence thing is. How much is the vector field trying to flow out from that point? And so to calculate that, to get an idea of what that is, we're going to add together all the partial derivatives. So it's going to be partial f the partial derivative with respect to x of p, right? Partial x plus the partial derivative of q with respect to y plus partial derivative of r with respect to z. Right? Make sure I get that right. Yeah. Okay. So that's going to be, well, partial derivative of p with respect to x is going to be 4x cubed. Partial derivative of x with respect to y is going to be 0. Partial derivative of r with respect to z is going to be 4xy squared. So that is what we're integrating over e. It's going to be 4x cubed plus 4xy squared dv, but dv is just going to be, well, let's say dv for a second. dv. So of course we could turn this into a just a regular integral with like rectangular coordinates. So let me show you what it is in rectangular coordinates here. So the in rectangular coordinates, it's going to be triple integral over e. Well, I guess not over e anymore because I'm going to put the bounds in. Plus 4xy squared. I'm going to do dz first. dz, dx, dy. That's what I'll do. So now, first bounds x. What is bounding our x? Oh, sorry, first bounds are z. Z is what's bounding our z. So the bottom bound, if you're imagining that volume that's enclosed there in that space, right? the lowest value you can have visually, the lowest value is at z equals 0, right? That's the lower bound of that region. If you said like, I need to put a cap on the bottom of it, it would be just the plane z equals 0. So 0 is our bottom bound there. And the top bound is that plane that's intersecting. That plane is x plus 2, right? Given to us as x plus 2. Right? Okay, so I know that so far. Then I want to find dx. Oh, I want to find the bound for x, right? So for x, let me see how I did it here quickly. X. Yeah, okay, we can do that. That's fine. So if I were to like look at a top-down view of this, right, it's really just a circle, right? A circle with the equation x squared plus y squared equals 1, right? So it's a cylinder, but if we're looking just straight down, it's just going to be a circle. So from here, I want to figure out how x varies. What are the two bounds of x? So I'm going to solve for x here. Right? There's my x-axis. I'm going to solve for x. X is equal to 1 minus y squared plus or minus that. And what that means is that the two bounds for x, the two bounds for x look like this. There and there. Yes, I think it'd be better to use z r d r d theta. Yeah, dz. Yes, it will be. I'm just showing to do it in rectangular, and then I'm going to convert it to polar after. Yes, I will do that. So from here, we're just gonna, there's our two bounds, right? The x bound is the lower one, so this right here is going to be your negative root 1 minus y squared, and that's going to be your root 1 minus y squared. And there's your two bounds on x. So x goes from negative root 1 minus y squared to root 1 minus y squared. And finally, y, well, y, if you just look again here, right? What's the highest and lowest value for y? Well, it's a circle of radius 1, so negative 1 and 1. So it goes between negative 1 and 1. And there we go. Yeah, it's solvable in rectangular, so you could do this. It'd be pretty hard to solve it in rectangular. Especially when you get to this part here. You got to do some crazy stuff there. I mean, not crazy stuff. Probably just some trig substitution or something like that, but you definitely have to, dust off the calculus 2 notes to figure out those integration techniques, right? To do some of these integrals. So we're going to convert it to polar in order to better understand what's going on here. Actually, sorry, we're going to convert it to cylindrical. Okay. Sorry, I was saying the wrong thing there. So this is essentially how you convert something to cylindrical. So I'll say convert to cylindrical. And we can go ahead and try to do it here. So our bounds of integration, okay, it's going to be triple integral still. dv, so I'm going to just say here, so this is how you would do it. This is the rectangular form. Right? So you can either go from this to this, or we're going to go directly to polar here. So polar is going to be good too. So to convert to polar, you need to use r dr d theta dz. Okay, but we will. I just want to see the order I did over here, right? Just to simplify the order a little bit, you'll see in a second why. But since we have bounds for z very explicitly, I'm going to put z first, and then dr, and then d theta. Okay. Yeah. Since we have very explicit bounds for z, 0 and x plus 2, right? Then we could do that. But I need to convert everything into polar form, right? So if I were right off the bat here, for the bounds, I'm going to deal with the inside in a second. For the bounds, z, I would say, okay, goes from 0 to x plus 2, but that's not in polar form anymore. I mean, 0 is fine, right? That just stays 0. But then I need to convert the upper bound into polar form here. Can we change the order of dz, dr, d theta? Yeah, we can change the order. I'm quite certain as much, like, with no adjustment. Yeah, with no adjustment. It should be okay. But this is just like this is just the form that I did it in, and it made sense, and it agreed with the solution, so I just went to it like this. So I got to convert x plus 2, sorry, to be clear, I got to convert z equals x plus 2 into polar. Sorry, I keep saying polar, right? Cylindrical. Let's just see what they did here. Okay. So to do that, I just do what they're saying. Z equals r cos theta plus 2. And there we go. It was that was simple, right? Now it's in polar form. You just follow these conversions right here. So the upper bound is going to be r cos theta plus 2. Now for r is our bound here. Let me make sure I'm doing it right. Yes, r is our bound here. So how should I explain this? To think about it, right? Convert the region. Okay, so you want to convert this bound here, essentially, right? You want to convert this bound here, this circle here. That is the bound in your x and y plane, if you're looking flat down, right? Well, remember, x squared plus y squared in cylindrical, if I just convert x squared plus y squared equals 1 into cylindrical, right? Let's see what we get, right? Let's see what we get as our thing here. Well, it's going to be, I mean, I'm sure you already know. So r squared cos squared theta plus r squared sine squared theta equals 1. Right? Factor out the r squared, you get cos squared theta plus sine squared theta equals 1. Right? This goes away because it's just 1. And so we get r squared equals 1 or r equals 1. Well, r equals plus or minus 1. But for the sake of since you can also rotate r, we can just say the maximum length that r will have is 1, and that's because it's stretching out here to meet the end there, right? On this plane, on this so we kind of changed the plane here to r plane. So r goes to make any vector here, right? To make any ray like this, right? The maximum length r will have is 1, and the minimum length r will have is 0. And then to fill in that whole space, we want theta to go from 0 to 2 pi because we want this angle to be able to go all the way around, right? And what's happening, you kind of imagine like the vector can go the length of r. I wish I could draw this somehow, but the length of r, like picture you're at the origin, right? And then the length of r can go on the xy plane, from 0 to 1 in any direction, any of these 0 to 2 pi directions. And then from there, the z value of the coordinate can go all the way from 0 to r cos theta plus 2, which is that other plane. And that gets us our bounds on the integral right here, right? And so this last point is just because the cylinder is a circle, right? Fills a whole circle. And then we get that like that. So yeah, there's that. Okay. Then I've dealt with the bounds. I need to now deal with the inside, right? So I'm just gonna put here. I'm just gonna put question mark, question mark, question mark for now, just to note that I'm not leaving it blank on purpose. I gotta convert all that to polar now, right? So let's just say I'm gonna convert this to polar. I keep saying polar, but I mean cylindrical. Okay, so let's go ahead. 4r cubed cos cubed theta plus 4r cos theta plus, it's not plus, sorry, r squared sine squared theta. Okay, let's simplify it a little bit. I'm going to factor an 4r cubed out from both. I'm going to get cos cubed theta plus cos theta sine theta. Okay, and then to simplify it a little bit more, sorry, sine squared theta, I'm going to write it as this: 4r cubed cos cubed theta plus cos theta times 1 minus cos squared theta. The reason I'm doing this is because now this cos and this cos squared are going to multiply into cos cubed with a negative sign, so it's going to cancel, right? That's a convenient part of this question here. So it's going to be 4r cubed cos cubed theta plus cos theta minus cos cubed theta. Right, those are going to cancel, and it's just 4r cubed cos theta. So that is our question mark, question mark, question mark. Very good math notation. And so now if I finally go over here, plug this in. Oh, no. OneNote is being annoying. Here. OneNote is always annoying. Okay. There we go. So what am I doing? Whole circle goes away. That goes away. Question mark, question mark, question mark goes away. Move that over there. Okay. So now we just put that in for r cubed cos theta. And so finally, to integrate this, we're just going to say the integral from 0 to 2 pi, integral 0 to 1, integral 0, r cos theta, oops, plus 2. Put a 4 in the front, right? It's r to the 4 cos theta. Perfect. There we go. Okay. And I actually didn't integrate this on my actual go, so let's see, like when I did this, so let's see if we're able to integrate this properly. I just said, okay, I got to here and I checked the answer and it was right, so let's go through it together. Let's see. 4 integral 0 to 2 pi integral 0 to 1. There's no z in this, so it's just r to the 4 cos theta, right? And then I'm just going to multiply that by, well, I'll just show you, right? It's going to be times r, well, what's r cos theta plus 2 minus 0, right? dr d theta. So essentially that block turned into that, but we just took that out because it's constant to the to that integral because there's no z in there, right? So then we have just 4 integral 0 to 2 pi integral 0 to 1 of r to the 4 cos theta times r cos theta plus 2 dr d theta. So 4 integral 0 to 2 pi integral 0 to 1. Okay, so r to the 5 cos squared theta plus r to the 4 cos theta 2 times that dr d theta. Okay. Now again, we just do. Sorry, I might, you gotta forgive the handwriting. If I ever write anything that's so messy you can't read it, just tell me and I will rewrite it. But I think you know what the integral sign is. So then now I'm gonna integrate this with respect to r. So it's gonna be r to the 6 over 6 cos squared theta plus 2r to the 5 over 5 cos theta. That's fine. Evaluated 0 to 1 d theta. R integral 0 to pi. Now, evaluated at 0, I can just forget about that. So I'm just going to evaluate at 1. 1/6 cos squared theta plus 2 over 5 cos theta d theta. Okay, and I'll break this up into 2 integrals, right? So 4 over 6 integral 0 to 2 pi of cos squared theta. Wow. Cos squared theta d theta, right? Plus 8 over 5. Importantly, you got to multiply the 4 in there. Integral 0 to 2 pi of cos theta d theta. Okay. And then from here, we need to integrate cos squared theta, which means we need to use that formula, which is on the thing here, but now I have something blocking it. The formula is 1/2 cos squared, 1/2 cos 2 theta minus plus 1. There you go. So that's a 2 over 3 integral 0 to 2 pi of 1/2 cos 2 theta plus 1 d theta plus 8 over 5 times sine theta evaluated 0 to 2 pi. Sine of 0 is 0. That's right? Yeah, sine of 0 is 0, sine of 2 pi is 0, so that goes away. And then here we have just this to deal with. So 1/3 integral 0 to 1 of cos 2 theta plus 1 d theta, which I will break into 2 integrals again, of cos 2 theta d theta plus 1/3 integral 0 to 1 d theta. So this is going to be 1/3 1/2 sine 2 theta evaluated 0 to 1. Yes, 0 to 2 pi. Thank you. I don't know where I got 0 to 1 from. Yeah. 0 to 2 pi. It's here too. Plus, and this is just going to be 2 pi over 3. Right? And then here, that's also 0. So, right? That is also 0. Yeah. So it looks like 2 pi over 3 is our answer. Assuming I didn't make any mistakes in there, but I think I'm good. Yes, I actually am good. I checked this on Wolfram, and that was the answer. Okay, there we go. So there is the example of doing a divergence theorem question where we had to convert to polar, right, to be able to solve this. A cylindrical. Okay, we got 10 minutes left. I want to do a gradient question. How do we get 4r cubed cos theta again? 4r cubed cos theta. Where was that? 4r cubed cos theta. This part right here. I converted the this, which was I converted this to polar. Sorry, I converted this to cylindrical. What is this? This is the argument of the integral, that thing there, right? So I converted that to cylindrical by replacing it with all these substitutions, and then there. That, if you want to take a screenshot or something, there you go. That's how I did it. Right? I mean, this is correct. It's just not very simplified, right? You probably want to simplify as much as you can, and see whenever you can make cos squared, sine squared plus cos squared. You know, you want to make that whenever you can, because obviously that's 1. So, okay. If there's any more questions, let me know. I will open up the last question we got time for. Missed that, and this question was 100 times. So yeah, you missed that solution there. Yeah, it's a tricky one. Let's do the potential function. Yeah. So question 7 on the practice exam is about finding a potential function. So let's give it a try. I'll show you generally my method. I wrote it in here, so I do have it written. It's the yellow one here. So here's it is for R2, and here it is for R3. It's a little harder for R3, but that's the idea. I will have it open because I do need to follow it. Essentially, the idea is that, question, what's a potential function? Potential function is essentially, it helps us with the fundamental theorem of line integrals, which is telling us that, it doesn't have to be a circulation. Let me just find it quickly. This fundamental theorem of line integrals is saying that if I have a line integral, right, over C of some vector field dot dr, then that's equal to f of the starting point, so f of the endpoint minus f of the starting point. But what's this f? Right, I'll say what's this f, right? It's f is not equal to the vector field f. It's a scalar function, right? But essentially, it's what we say is like the gradient of f is equal to f, right? The gradient of the scalar function f is equal to the vector field f. And so we say that f, this f, the scalar f, I'll call it scalar f and vector f. So scalar f is a potential function, for f, like that, right? So yeah, some people, I missed that during class, but I don't remember hearing it before. Yeah, so that's what it means. And so this is the fundamental theorem for line integrals. It's very useful here because if we know a potential function for f, it's really written like this, right? Like the line integral of the gradient of f dot dr is equal to f of the endpoint minus f of the starting point, right? But you know, to do this, you need to say, okay, well, what function has a gradient of f? Nabla is not like the symbol does not necessarily mean it, but like the gradient of f, this is the gradient of f, like that. Right? Yeah, okay. Nabla is just like the is like the Greek letter. That's the Greek letter, Nabla. right? But nabla F is the gradient of F. Exact condition thing, well, so we can check if there is a potential function by doing the exact condition thing. But given by the fact that they said by finding a potential function, we don't really have to do that. But yeah, this is where you would use exact conditions to check it. Like if you didn't know that there would be a potential function for this, then you could do that to figure it out. So let me put it here. There's a few tests, right? So it's not really just one test for if a potential function exists. So a vector field that has a potential function is called a conservative field. And so there's a whole bunch of tests to see if a field is conservative. It's essentially the same thing here. I'll put it up here. It's essentially the same thing as saying like, oh, this scalar function is integrable, right? Integratable on something. But the condition for that in the scalar functions was just that it was continuous. If it's continuous, it's integrable. But here there's much more condition for it to see if it's integrable, right? So yeah, we can check if it's conservative, right? Doing this, right? I mean, there's some technicalities here that, there has to be there's a little bit more to say before I can say that, if it passes this, it has to pass a few more conditions, but I'm quite certain for the sake of this exam, it won't be like that. Although I could talk about it after. But yeah, this is essentially the condition for checking if it's conservative. And so, but we don't have to do that because it says that, we do it, but that's how it is. Like it says it's going to be, we're able to find it. So now the challenge really is finding the potential function, right? And so we do that by looking at this, and we, note by what we see here, we know that this right here is going to be P, this is going to be Q, and this is going to be R. So whatever the gradient of F is, it's going to be equal to PQR. And we're essentially trying to solve for F. We're trying to solve for the scalar function F, whose gradient is PQR. So let's make that equation. Gradient of F is the partial derivative, well, I'll say Fx, Fy, Fz, that's the gradient of F, is equal to 3x sine y plus e to the 5z, okay, x squared cos y, that's it, and 5x e to the 5z plus 1. So we get this, and we have essentially 3 equations and kind of 3 unknowns. Well, you'll see in a second how we have 3 unknowns. And so we can solve for the function f here. Okay, so we'll start with fx. So fx is equal to 3x sine y plus e to the 5z. So what we're going to do is we're going to integrate both sides with respect to x, right? With respect to x. So 3x sine y plus e to the 5z dx. Okay, and if we integrate both sides with respect to x, here we get just the function, right? And then here we get this. This question has an error. P has 3x squared, not 3x. Q has x cubed, not 2x. With that, it should work. Oh, there was an error in this? Okay. P has, so this should be 3x squared. And Q has, okay, and Q has x cubed, not x squared. So that should be like that. That's what you're saying? Did I get it right there? Yeah, it is annoying that they have errors in this. Did I get it right here based on what you're saying? That works out? Okay, good. So that is important to change. So let's see if that works. So it should be a square, that should be squared. Okay. Make sure that I got that right. Squared, and it's cubed, and da-da-da. Okay. Integrate with respect to x. We get, well, that's a constant, that's a constant. So it's just going to be 3x cubed over 3 sine y plus e to the 5z x. Yes, I'll show you that. Show that formula again. Which formula was this? That
one. Yes, that
this
box.
One? Okay.
Thank you. 1 second.
Sure, no problem. Okay.
I'm good. Thanks.
Okay, sounds good. So then now what's my constant? So my constant is actually some function of both y and z, right? So I forgot what label I put it on, so let me just find the label quickly. No, I went too far. Where is it? There it is. Just want to stay consistent with my notes here, right? So it's going to be plus h, I'll just call it plus h of yz. It's a function of both y and z, because if you take the partial derivative of this with respect to x, it's just going to cancel out, right? So when I integrate it, instead of having a plus c, it's going to be a plus h of yz. And so there's like an unknown that we have to solve for, right? This is definitely the beginning of f, the function that we're looking for, but there's an unknown here. We got to solve for that unknown. So the next equation we can make is, so this is the equation created with fx equals p. The next equation we want to make is fy equals q. So for fy equals q, we're just going to get, well, fy equals, and then q is x cubed cos y. So x cubed cos y. And the thing is that we can determine both sides of this equation now based on what we got earlier, right? This side we already know. So when I said both sides, I guess I was thinking we have a q there, right? But this we can determine from earlier here. We don't have to also integrate this. We can just plug in what we got earlier. So fy, the partial derivative of this with respect to y, sorry, these threes would cancel, is going to be, well, x cubed cosine y, right? This goes away, right? And then we would just have some hy of yz, right? Derivative of that with respect to y. Right, so again, this is just the partial derivative of that equation with respect to y. And that's equal to x cubed cos y. And if you look at that, right, we get that hy, so just to be clear, that's not h times y, that's the partial derivative with respect to y of yz is equal to 0. Okay, and then we can integrate this to figure out h of yz. So if I integrate this with respect to y, yz equals, and so I integrate it with respect to y, a function of both y and z. I'm going to have another function, okay? I'm going to have another function, which I'm going to call p of z, and just z. Because if you were to take the derivative with respect to z and go back, with respect to y, I mean, and go backwards, you would get this equation. So you really have this unknown function of z here. Okay, I think there is a quick announcement that we have. Yes, there we go. I was just about to say, I think it's a quick announcement that needs to be said. So everybody take a look at the chat. I'm going to finish this question, but the tutorial for rest's sake is over. So yeah, there you go. There's a feedback form, everybody. You can take a look at the feedback form, and I appreciate you filling that out, and there you go. It appears there's an issue. You've already responded, so maybe take a look at that. I will continue solving this question, however. So now that I've determined that h of yz is equal to p of z, right? Just some other function p of z. I can go back up to this equation. Back up to this right here, which was the original thing that we found. Right? And I can now replace h of yz. H of yz is actually just a function of z. It's x cubed sine y plus e to the 5zx plus p of z. And finally, I can say fz is equal to r, right? That's the final equation I can make. I'll do it in a different color. Fz is equal to r. And that will let me solve for p of z. So it's like we have three unknowns, really, but slightly different. So fz is equal to 5x e to the 5z plus 1. So 5x e to the 5z plus 1. And fz, well, we just take the derivative of this with respect to z. And all that's actually going to be is p prime of z. Oh, that's not true. Never mind. Sorry. There's another term there. So that term cancels out, and it's going to be 5x e to the 5z, right, plus p prime of z. And from here, we can just see that p prime of z equals 1. So integrate with respect to z, we get just p of z is equal to z plus c, right? And that's just a c now. Right? It's just a regular integral here. And I can go now back to my equation here for f, which we knew in terms of that little extra constant p of z. And we get our final answer. So f, the potential function, is x cubed sine y plus e to the 5zx plus z plus c. And the gradient of that function is equal to our vector field. And so we can now use this to determine the line integral like this, right? The line integral like that, by just using the fundamental theorem of line integrals, or for line integrals is really what you call it. And what we do is we just evaluate, so that integral is equal to f of 3 pi over 2 5 minus f of 1 0 0. Right? Just like you do regular integrals, right? You just do that. And so this is going to be 3 cubed sine pi over 2 plus e to the 5 times 5 times 3 plus 5. And then we don't need the plus c because it'll cancel, right? On both sides, so we don't need the plus c. Just like with regular integrals. Minus f of 1 1 0. So it's going to be 1 cubed sine 0 e to the 5 times 0 times 1 plus 0. It's all that there's a plus there, sorry. There's a plus, yeah. So I think it's just minus 1. So that's going to be 27. Sine pi over 2 is, I can't remember sine pi over 2 at this moment. Sine 90. Yeah, 1. That makes sense. There you go. So plus e to the 25. So 3e to the 25 plus 5 minus, well, that's obviously 0. That's 0. So we just have, that's 1. So it's just minus 1. So I got plus 4. So 31 plus 3e to the 25. And I certainly hope that's the answer. Yes, that is one of the options. So I would be surprised if it wasn't. There you go. That is one of the answers. Okay, feedback form is back in the chat, so everybody take a look at that. This one will work. And that is the end of the content that I wanted to cover for today. So perfectly on time with everything. Hopefully this was helpful to all of you. If you have any questions, I'll be here for a few more minutes to talk about things. But otherwise, have a good night. Good luck. And no problem. No problem. Have a good night, guys. Good luck on Monday. Good luck on 318. Everything goes well. And again, I'll be here for just a couple more minutes to answer some questions if anybody has. But otherwise, have a good night. Can I go up a little bit? Yes, I can. Go up. How far up? 318 session is tomorrow, yes. I'm very happy to hear that was helpful. Hope you do well. Everything goes well. Tell me when to stop going up. Just the last part of the question? Yeah, so if you want the textbook, just here, message me on Discord. And there you go. I can get you the textbook there. Okay. Any last minute questions, let me know. I will stop recording.